So it's a pleasure to be here at ICTS. This is my first time. Do I need to be in one place? Do I need to be in one place standing, or I can move around? Okay. So it's a pleasure to be at ICTS. I have not been here before, but my career in fluid dynamics started at TIFR in Bombay. It was Bombay that time. In 1985, when I did the summer internship with SM Chitre on convection zone modeling for the sun. So that was my first exposure to fluid dynamics. And at that time, I was doing things like string theory and particle physics at IIT Kanpur. And this exposure to fluid dynamics, and also I did an earlier project on the Lorentz system and chaos. And I started thinking about applying physics to those domains. And so I went to do my PhD in climate modeling. And I've been doing climate modeling since that time. And so it's a pleasure to reconnect with the physics crowd in some sense, going back to my roots in physics. So I'm going to talk about current developments in the numerical modeling of the Earth system. So I've worked with models of varying complexities, starting with the Lorentz system all the way to full Earth system models. And I'll share with you some of what I know about the current state of affairs and what are the challenges we face in Earth system modeling. I'm going to give a slightly philosophical description of things. I'm not just going to say what we do, but ask why we do that. And that gets into a bit about philosophy of science. But that gives you a better understanding of why we do what we do in climate modeling. So what you see in this introductory slide on the top left is a grid. That's a model. And the top right is a projection from the model. So we're taking the Earth, we're discretizing it, putting it on a grid, and trying to predict what the future holds for us. So that's the challenge we face. So as I said, I was working on string theory and particle physics when I was finishing my master's. And I know one of the big things at ICTS is string theory. String theory is sometimes called the theory of everything, not necessarily in a flattering sense, but so the theory of everything has a nice ring to it. If you're a scientist and you're working on the theory of everything, it's sort of a grand thing to do is to work on string theory. And there was this movie about it, about Stephen Hawking doing the theory of everything. So when you think of climate modeling, in some sense, it's the model of everything. If you think about it, pretty much everything that you interact with, everything you know about has to be in the model in some sense, okay? So string theory may be theory of everything, but it's a theory of lots of small things at very, very small scale. But the model of everything is pretty much the globe, continents, the atmosphere, the oceans. They're all large things, but there are small things within them. You have turbulence occurring at microscales, aerosols, which are at micron scales. So it is actually truly a model of everything that we build. And it's very daunting to think about, can we do a model of everything? And this is a question that came about. So this is sort of the, when you think of climate, it includes the ocean, the atmosphere, it includes humans. Actually, we talk about that. They're an important component of future climate. It includes dust, marine organisms, plankton, all of that. So recently in the US, there is some polarization about climate, more so than in many other nations. So you have climate deniers and people who believe in climate. And so there was this Canadian psychologist, his name is Jordan Peterson. So he went on a very popular podcast show called the Joe Rogan Experience. And he basically said, you can't model everything, so you can't predict climate. That is, so the basic statements he made were, climate is about everything, but your model doesn't include everything. How do you decide which set of variables to include if it's about everything? So basically, climate models are useless. So that was his logic, okay? So in my talk, I'll talk about how that sort of it's a nihilist view of saying we can't do anything. The question is, how do we model everything, but you truly can't model everything? So what we do is we model everything that's important, right? And so the science comes in when we decide what is important. You don't model very small things because they're not important, but some small things are important. So if you have photons going through the atmosphere and getting absorbed by carbon dioxide, that is important, even if it's very small. But there are certain gases which don't have a signature in infrared, they're not important. So use science to decide what is important, and then you model an approximation of everything. So that is what climate modeling is about. You say climate, but includes basically everything that you interact with. And if you remember Dr. Dubos's talk, he said the challenge of climate prediction and policy is the scope and the scale. The scale goes from microns to planetary scale. And the scope goes from every activity that humans are involved in. So that is the challenge of modeling climate and also of mitigating climate. So when we do climate prediction, you have some quantity of interest. It could be the global mean temperature, and you have time, and you're trying to predict how it's going to change. So you have the information from the past, okay? And at some point at the present, you want to predict into the future. So you could take a spreadsheet, do it on Excel, and draw a straight line, okay? But then you get into issues like, how far back in time do you fit it? Sometimes a parabolic fit may be appropriate. And sometimes it may flatten out, it could be a sine wave. And just looking at this curve, you can't really tell which it's going to be. So sometimes looking at global mean temperature is misleading because you could just do an extrapolation. But the global mean temperature is an average of millions of local temperatures, okay? So you need to know the science behind this single variable to be able to predict climate. So you can't just do an extrapolation because you don't know if it's going to be parabolic, it could be exponential, it could be sinusoidal. And looking deeper into what's behind it is needed to predict climate. So I like to use a quote from oceanographer Carl Wunsch. He basically said, if you want to make a prediction, there are two ways to do that. Make sure that you're in sample. That means you have statistical data, and what you're trying to predict isn't the sample of what you have. Then you don't need to do any physics. You can use pure statistics. You can use a regression model, multivariate regression model, and machine learning, which is advanced statistics, to predict. You can have zero understanding of the physics, you could still do it. But if you don't have the prediction in your sample, then you need to know the differential equation. The differential equation tells you how a variable is going to change in time, and a bunch of variables that interact with each other, how they'll change in time. So when you do a prediction, you have to decide which one you want to use. And this leads to endless confusion because the word model is used for both. Dr. Dubos was talking about models, but many of them fall into the in-sample model where you have data about how price elasticity or how energy is going to change. You think it's an in-sample, but if you go out 70 years, it's not in-sample anymore. So that was the problem he's talking about. You can't just extrapolate because it may not be a straight line. But in climate, we still call it a model, but it's a very different type of model because it's a differential equation type of model, basically. So you know how the air is going to move, how the water is going to move, how the radiation is going to be absorbed, and you have equations describing all that. And if you know the initial condition, and we also know the boundary condition, you can solve it as well as you can with the computer that you have. If you have a bigger computer, some of those things you can solve better, but you're limited to some extent by computers, and also by things which you can't really do the differential equation for. Something like plankton, you don't know an exact differential equation for it. Or tree absorbing carbon. You have approximate equation for forests, but you don't have an exact equation like you have for a molecule or statistical mechanics or fluids. So it's a hybrid, but you start with the differential equation and you try to solve it as best as you can. So just to set some context, we are interested in climate change because we started observing carbon dioxide starting in 1960, and this is a famous Keeling curve. When he started measuring it, within about a decade or two, he found it was going up monotonically. And the wiggles are the seasonal cycle where the land absorbs carbon when plants grow, and when plants die, it comes back. So you can see the wiggles of the seasonal cycle, but every year the seasonal cycle doesn't come back where it started, it goes up a little higher.
So I have a quick question because this graph has come up many times. It seems to be sufficiently kind of, I guess, deterministic that you would hope that a model can replicate it. So can a model replicate the wiggliness in this?
Oh, the wiggliness, yes, yeah.
Can replicate now.
I'll talk about it. It talks about the carbon sinks in the atmosphere and the ocean. There's some uncertainty, but we can get the seasonal cycle of carbon dioxide.
Because I guess we heard in the morning from Srinivasan's talk that there's natural variation in models in the real world.
Right.
Now, can the climate models capture that natural variation? I guess that links to this question.
Only in statistical sense, not in a deterministic sense. Yeah, you cannot do that because the predictability limit only lets you predict up to 2 weeks. But in statistical sense, you can get the whole point of climate is you're not predicting weather, you're predicting the statistics of weather. So in a statistical sense, climate models can get it, but they cannot get it individually, in individual realization.
Because these variations look like they were on the scale of years, you know. So
yeah, I'll talk about that in a moment. But one thing is, because of COVID, emissions went down dramatically, like 10, 20%. And that'll lead to flattening of this. And I think models should be able to capture some of that. So models can do those kind of things. Predicting carbon dioxide is one of the easier aspects of climate modeling. Predicting natural variability is much harder because it's much more stochastic. So we have the Keeling curve, which shows carbon dioxide is increasing. And we have, this is the global temperature from 1880. What you see is the temperature rose a little bit before 1980 or so, 1970, and rose a lot after that, and it seems to be accelerating. And carbon dioxide had been measured from 1960, and you can see there's a correlation between these two, okay? But you can have correlation between any monotonic curve and anything else. We plotted the stock market index, again, you can have correlation. So that is not enough by itself to make a causal relationship between the two. And one of the questions we'll ask is this sort of increase in sample, okay? So remember, if you want to predict, you can do in sample statistical models or difference equations without a sample. And actually, Dr. Srinivasan already answered this question in his talk. I'll just repeat that. So this is basically the curve he showed. The solid line is carbon dioxide from the Vostok ice core. And the gray line here is the temperature change, inferred temperature change. And if you superimpose the Keeling curve on this, you can see you flatten the time, and it looks like a vertical line because it's very dramatic. The rate is unprecedented. So the rate of increase of carbon dioxide is out of sample. That's a point that Dr. Srinivasan explained, that you're talking about something unprecedented. So we can't simply use a statistical model because we don't have such a rapid occurrence, that much of an increase in carbon dioxide occurring within a century. So we need to start with differential equation-based models. If this wasn't the case, if carbon dioxide was increasing about the same rate, we could try to use more statistical models, but we can't do that. Again, this could trigger tipping points because it's happening at such a rapid rate. So how do we attribute the global warming to carbon dioxide? And this is more of a detail to what Dr. Srinivasan showed. He showed a couple of these curves, but we can add some more detail. So the black line is what I showed you earlier. That is the global mean temperature since 1880. And if we build a climate model and put in all the factors, that is circles here, open circles, and it captures the rough tendencies. It can't capture the exact wiggles because there's some natural variability and model errors. But if you put in all the factors, the model reproduces observations. So this is one of the ways in which we check climate models. But there's something you can do in a model which you can't do in the real world, is to decompose the different factors that contribute to this. As I said, just looking at a scalar variable, you can't really predict what's going to happen in the future. You need to look at how it adds up to get to that point. So what we can do in the model is keep only the greenhouse gases and take out aerosols, which are things like sulfates, which reflect sunlight. So if you take out the aerosols and just put greenhouse gases, it warms more than observations, okay? But if you put in just aerosols, but no greenhouse gases, it cools. And this is basically industrial activity generating sulfur dioxide and other pollutants, which cool. And this cooling is compensating some of the warming, and you're getting this agreement with observations. And Dr. Srinivasan mentioned, in the future, you'll clean up and you remove this pollution, it's going to amplify the warming. The other issue that keeps coming up is people will tell you, but sun is driving climate, so sun may be driving this. And actually, there's a quote from Suki Manabe, he said he started studying carbon dioxide in his models because it's the second most important factor driving climate. First is obviously the sun. But the sun has to change to affect climate, and with satellites, you can measure how much it changes in the last 20, 30 years. And based on that, you can put that forcing in the model, and this is the response you get. So you can see a response, but it's very weak. So pretty much everything is going to affect climate. It's the question is which is big and which is small, and what's important, what's not. So you could build a climate model without the solar variation, you basically get the right answer. So you don't have to model everything. You only need to model what is important. And these are obviously important: greenhouse gases and anthropogenic aerosols. Volcanoes are important when they erupt. So you can get like a 0.5 degree or 1 degree cooling. These are major eruptions, and they put sulfates, and they can cool the atmosphere. So this gives us the confidence that carbon dioxide and other greenhouse gases are driving climate change. So how do we model it? And how do we try to predict what's going to happen in the future, whether it's going to accelerate, whether it's going to go in a straight line, whether it's going to even out? Okay, so we need to build a model based on science. So just to reiterate, we need to predict an out-of-sample warming. So we can't just use a statistical model. We cannot predict everything, but we don't have to. So we start by predicting things for which we have accurate differential equations. And that we start with the Navier-Stokes equation for motion of air, motion of water. And we can put it on a grid and solve it using math and put it on the biggest computer we have, and we can predict how air and water are going to move. But there are certain things which we cannot put exact differential equations, like clouds. Model grid size won't resolve a single cloud, which is about 1 kilometer in size. So we put approximate differential equations. Sometimes we call them turbulence closures or the equivalent. Aerosol, they're micron scale. We'll never have a model that has a micron scale grid. Certainly not in my lifetime, probably never. But you have to put approximate differential equations for those. And we have things like trees and marine organisms. So again, we construct approximate differential equations based on data we have. But they suffer from the same problem Dr. Dubois alluded to. For a certain ecosystem now, you get certain relationships, but they may or may not be valid 70 years from now. So that you have to assume that it will be roughly valid to proceed. So there are errors you start introducing in that process. And then we just established that carbon dioxide leads to warming, but human activities emit carbon dioxide. So to predict climate, you have to predict what humans will do. And that's actually what Dr. Dubois was trying to do. In climate modeling, we don't try to predict climate. We don't try to write differential equations for humans, which some people are actually trying to do that. If a differential equation tells me I should go this way, I can decide to go that way, right? There's a problem with trying to predict human action because we have free will. In climate models, we don't do that. I'll talk a bit about what we do. We just basically assume what humans would do. We don't try to predict. So that's the way we get around this. So we do predict things which we can predict, and we assume things which we cannot predict. So just to give you a flavor, because this is an audience which may not be used to climate modeling, just to intimidate you, here are all kinds of processes that you need to put in a model, okay? It's just to intimidate you. You don't need to pay attention. There's deep convection, sensible heat flux, soil properties. And this is probably an underestimate. A modern Earth system model probably has 10 to 20 times more of these processes. This Tsuki Manabe's model probably had maybe 10, 20 processes like this, like 30 years ago. But modern models have much more than this. Yeah. I just put the atmospheric thing. There's ocean, there's land ice and sea ice, and yep, it's a lot more than you'd care to know. And so if you look at the big picture, so this is what a modular view or a schematic view of a Earth system model looks like. So this is a model I'm familiar with, the Community Earth System model from NCAR in Boulder, Colorado. So these are the main components of a state-of-the-art Earth system model. You have the atmosphere, and most climate modeling started with the atmosphere. Actually, since we had the Turing Lectures, interesting connection between Turing and atmospheric modeling. So Turing came to visit Princeton in around 1936 or so, spent a couple of years there. He was invited to come by John von Neumann, who was at the Institute for Advanced Study had just been set up, but it was actually located in the Princeton University campus because they didn't have a building. So von Neumann invited Turing to come to Princeton, and Turing did his PhD on some computational problem. But von Neumann got very interested in computing when he talked with Turing. But Turing left Princeton after 2 years. He basically wrote to his mother saying, with people like Einstein down the hall, I feel I'll be unappreciated, and he went back to England. Okay, people like von Neumann and Einstein were too big for him to handle. But von Neumann got interested in computing, and he decided to build a computer at the Institute for Advanced Study to predict weather. He was doing all kinds of things, predicting shock waves for nuclear explosions, but he really wanted to apply science. He decided to predict weather because he said, we know the differential equations, we'll just solve it, but we need a computer for that. And he tried to build a computer IAS, just slow, and then he used the world's first computer in ENIAC, it was in Aberdeen, to do the world's first weather forecast. And then that was basically the beginning of using differential equations to predict weather. And then he said, if I can predict weather for the next day, I can run the model to infinite time, and that's climate. It gives you statistics of weather and stuff. So then he built this lab in Princeton. He started it to predict climate by just running an atmospheric model indefinitely. And you don't simulate weather in the future, but you simulate the statistics of weather, which is climate. So Turing sort of inspired this line of thinking using computers to solve differential equations. So atmosphere is where climate modeling started, but then people realized that if you run a model more than a month or so, heat capacity of the ocean becomes important because the ocean temperatures can change. Ocean temperatures don't change much within a day or two, so you can do a weather forecast assuming the ocean temperature is constant. It's not a bad approximation. Like a hurricane forecast, you can do that. When we're running it about a month, heat from the atmosphere can change the ocean temperature, so you need to represent that. And land you need too, because land also can change in temperature and can evaporate water. So you need the ocean, and then you need land. Land can evaporate water, it can provide friction in terms of trees, if you have mountains. You have river runoff that goes into the ocean, and then sea ice, because you have the Arctic is covered with sea ice. And the latest addition to climate models is land ice, like ice sheets, like the Greenland ice sheet or Antarctic ice sheet. Until recently, they didn't have land ice models, they would just prescribe it. It's very complicated to do land ice. You don't even know what's going on inside a 3-kilometer thick ice sheet. So all these components talk to each other through a software called coupler. So that again? Oh, these are things like if you have a hurricane, it creates waves in the ocean, and that changes the friction. So these are new additions to model. As I said, there are lots of new things in climate models now. So the coupler is basically like an exchange. So the atmosphere will send a heat flux to the coupler. The coupler will send it to the ocean, asking the ocean to either cool or heat, depending on the sign of the flux. And the ocean will do that and send its sea surface temperature back to the atmosphere, and the atmosphere will use that to decide whether to evaporate water, how much to evaporate based on the Clausius-Clapeyron equation. And then same with land for evaporation and friction. And then sea ice, you can put heat and melt it. And so each time step, each of them sends information to the coupler, and the coupler sends it to the right place, gets information back. And this happens every time step. In a modern climate model, the time step may be like 15 minutes or 5 minutes. Model time. So every 5 minutes model time, this exchange will occur on millions of grid points around the globe. So that's our model. So when you do that, yes, we solve the differential equation for each component, exchange between the different components, get to the next time step. Oh no, there's limits. We try to use the longest time step we can because for efficiency, but it's called the Courant-Friedrichs-Levy criterion for partial differential equations. So if you have a certain grid, and if you have flow on that grid, the time it takes for the flow to go from point A to point B, if the time step is shorter than that, the solution will blow up. It's a numerical requirement. Because it's basically information, if your air flowing from this point to that point, and if your time step is longer than that, you're not getting the information there. And ill condition, it'll blow up. So that determines the time step. Yeah, if you have V is the velocity, and delta X is the grid size. So delta X over V gives you a time scale, and that is your time step. And that's a mathematical requirement which you cannot violate. People are trying to do that in machine learning, trying to go from one type. Because machine learning is not subject to partial differential equations. So that's the only way you can do that. But if you're solving partial differential equations, you have to obey this criterion. So what happens is, as the grid gets finer, your time step gets shorter. I'm going to talk about it later. So if you double the three-dimensional grid, so you get 2 cubed more points, 8 times more points, but the time step gets halved because your delta X is halved. So you need 16 times more computation. So 2 to the 4 each time. So that puts a big constraint on the computational requirements of the model. Because it is developed not just by NCAR, but a community of university scientists. NCAR is run by the National Science Foundation, which usually does not fund research labs. but it funds NCAR as a facility to serve the university. NSF's mission is to serve universities by giving grants. But it gives a big grant to NCAR saying, help the universities do climate modeling because the model is too big to maintain on their own. So it takes 50 to 100 people to maintain a model like this and $50 to $100 million to do that. But what NCAR does is to build a model, but people who build these components often are from universities. So there are working groups where university scientists chair the groups. Like an ICE model, they might come up with formulations and they work with NCAR to put it in the NCAR model. So it's a community project, not just a one institution. Not all models are like that. There are other, like the three major models in the US are developed by NSF, National Science Foundation, the Department of Energy, which is the equivalent of DAE here, and the National Oceanic and Atmospheric Administration, which is probably like the Ministry of Earth Sciences here. And they each have a big model, but the DOE model is mission-oriented. Their goal is to do energy-related things. They don't serve the universities. And the NOAA model is environment, ocean and atmosphere related. And their mission is to serve weather forecasting and things, not universities. So they're not community models. So that's why. And for that reason, this is open source. And they have dedicated staff to help US university researchers to install the model. If there are problems with it, they provide a service to that. And if you're at the university and you come up with a tweak to the model that improves it, you can submit it to NCAR and have it approved and then included. And there's an annual meeting each year where several hundred people come and talk about the different components and how we can improve the model. So to give you a flavor for what the grid of a model looks like, and these acronyms stand for the IPCC reports. FAR is the first assessment report from 1990. Second assessment report was 1996 or so, 97. The third assessment report was like 2000, I believe. And you can see they didn't think far enough with the acronyms. I think they assumed they wouldn't be going that far into the future because this would also be FAR, the fourth assessment. They switched to AR4, and that was in like 2007, then we had AR5 in 2013, and then the AR6 was released in August 2021 for the physical component, and actually the adaptation component actually released yesterday for AR6. But you can see the grid, it was 500-kilometer grid in 1990, went to 250, 180, 110, this was around 2007. And actually hasn't changed that much in the last 20 years, last 15 years. It's about 100 and between 100 and 50. We got much faster computers, probably 1,000 times faster. But a lot of that effort has gone into adding processes, chemistry and ice and so on. The grid itself hasn't changed a whole lot. Yeah, so typically here it might have been like 10 or 15, and now it's more like 30 and sometimes 60 of that order. It could go up to 60 kilometers. If it's 60 levels, it could go up to 60 kilometers. With 30 levels, it's mostly up to 30 kilometers. Oh, full depth. You have to go full depth, which is wherever, 12 kilometers. But average, yes, 4 kilometers. In the ocean, again, you might have 50 levels. That's typical, 50 levels. And often the land grid is finer than this. This is the atmosphere and ocean grid. The land grid tends to be finer because you want to represent heterogeneity in land, because there are different land uses, like farmland, trees, forests, within a 100-kilometer box. And you have fractional grid boxes to do that. Yeah.
How much is the improvement of accuracy over these four models?
You get obvious improvement because like island nation, it wouldn't even be there in some of these, right? One of the important things is like the Andes. It's a very narrow mountain range. It's still not, even 100 kilometers is not enough to get the sharpness right. The Himalayas are not that sharp, but mountains, getting the rain right on different sides of the mountains, rain shadow, they all improve as you get finer grade. So they're obvious improvements. Yeah, I'm not going to show it, but the most recent models, the NCAR model and the DOE model both have what's called regionally refined mesh. So you could have a 100-kilometer grid globally, but over the United States or the tropical Pacific, you can have a 10-kilometer grid or even finer. And it basically, the mesh increases smoothly as you go in.
What about the grid which changes with time, like you put it where you need it?
For climate, you wouldn't do that. For hurricane forecasting, people try to do that, but they don't do it in practice because you have to interpolate, and that creates errors. But fixed refined grids are now there in climate models because people want to predict weather for their climate for their country at high resolution, but they don't want to run the whole globe at the high resolution. It gives you some benefit, but not all, because it gives you local. I mean, if you have a mountain and you want to get the rain right on the right side of the mountain, it gets you that. But the uncertainty globally still gets into that region. So just because you have high resolution there, you don't escape the uncertainty that's all around you, and that'll come back. So you don't reduce the uncertainty, but you get the detail right when you go to a regionally refined mesh. So let's start with the atmospheric model. This is a schematic. Actually, Tapio Schneider is talking, I guess, in a couple of days. So this is from his paper, which just shows schematically how an atmospheric model grid looks, like 30 levels, as I said. And this grid box could be 100 kilometers or 50 kilometers. But within a grid box, you have clouds, right? Let's say there's a 100-kilometer grid box. The cloud could be 1 kilometer, right? So you have the differential equation for air, but you don't have the differential equation for the cloud, so you'd approximate it. So people use physical ideas about plumes. Sometimes people use statistical models. Sometimes people run high-resolution models for the clouds and get machine learning out of that. And you put that into this. And this is called a parameter, subgrid parameterization. So you parameterize what you cannot resolve. This introduces errors because you're no longer solving the partial differential equation accurately. And for weather forecasting, if you're forecasting the motion of cold air, large, massive cold air, thousands of kilometers, you're solving it exactly, you get that right, which is why your temperature forecast is usually pretty accurate. But your rain, it's not just air, you need the clouds. So that's why your rain forecast is a lot less reliable than your temperature forecast. An interesting question is, what if your grid went down to 1 kilometer or 100 meters, and you actually are resolving the clouds? Will you get a much better rain forecast? I don't know the answer. People are getting to that kind of resolution. You probably see a 3-kilometer resolution within a few years, at least for short term. Yeah, actually, Rama can talk about it. Even if you're 100 meters, you have things like rain particles happening at micron scale, and whether you can get it right, that's still an open question. You can get the large-scale fluid motions right, but you have the phase transition happening at the raindrop scale. Whether you can get that right, I don't know. But so your weather forecasts for temperature are quite accurate because you get the large-scale motion right. I mean, if you're forecasting tropical cyclones, again, rain and the eye wall is very important, and the climate model won't get that right. Weather models now are running at 10-kilometer grid, so 10 times finer climate models. So our weather forecasts are a lot more accurate than they were 20 years ago, because you're going to a 10-kilometer grid. You really are resolving a lot of the fronts much better now. And I'm sure weather models will go to a 3-kilometer grid fairly soon. That's doable. The computer's getting faster. Oh, no, weather models do it globally. Because, for example, if you're predicting weather in the United States, what happens in China within a week will affect the United States. You can't do it locally because you need, so the world is interconnected. I mean, you could, I mean, yeah, like people do aviation forecast for the next 3 hours. You don't need a global grid for that because information isn't going to come from far away. But anything beyond a few days, you typically need a global grid. Right.
Climate model is larger, but they are both global.
Yeah.
That's because weather model is being run for.
Exactly. Yeah. Yeah. If you don't have the computer resources to run a 100-year simulation with weather models. Yeah. Actually, at Texas A&M, we had a center which worked with NCAR and with the Chinese lab. We are running at 25 kilometers for hundreds of years. So that's the highest resolution climate models have typically been running at. But I'll show you a picture later about DOE in the US is developing a 3-kilometer climate model.
Can you say something about the computational, I mean, the number of processors in parallel and?
Okay, I don't have the slide, but I'll tell you something when I come to that point. Yeah. So we need to represent the clouds, and that's one of the biggest uncertainties. Yeah. Yes, clouds parameterization is one of the biggest uncertainties. Clouds do two things. They reflect sunlight and cool the globe. They also can trap infrared and warm the globe. And that's a cancellation. So if you're talking about global warming, the net effect of clouds is one of the biggest drivers of uncertainty. At the moment, we think cloud in the net cool, which is a negative feedback. If they're warmed in the net, that would be a positive feedback. So clouds are uncertain. And even bigger uncertainty is interaction between aerosols and clouds. If you have a lot of pollution, how does it change the size of the raindrops? If there are smaller raindrops, it'll reflect more sunlight, and the cloud may live longer. So that changes the radiation budget. So if you look at the heat budget for the Earth, I don't have a picture, but IPCC puts these out regularly. Some of the biggest uncertainties deal with aerosols and clouds. And to give you a magnitude, the warming signal associated with doubling of carbon dioxide is 4 watts per meter squared, globally averaged. And the uncertainty associated with clouds can be about 1.5 watts per meter squared. So that's like 30% uncertainty just from that one process. So that is one of the biggest uncertainties when people try to predict climate out to 100 years, because this 1 watt per meter squared error can build up over time and give you a lot of spread in your predictions.
One more thing. So these are the models from the US, I suppose. So are there other models?
Yeah, I had a picture of how many models the IPCC uses, about 40 models. US has 3 main models now. UK has like 1 or 2, and Germany has one or 2. Most countries have 1 or 2 models. China, I think, finally got 1 or 2 models. They didn't have a model until recently. IATM has the Indian model. So most countries have about a model or 2. US has like 3, and that's so 40 or so models.
Is there like a good correlation between most models, or I mean, is there like a huge range of uncertainty arising from all these models? Or?
Yeah, I'll tell you a bit about that. Climate sensitivity estimates have actually diverged in the last IPCC report. You normally expect in models they'll converge. Right? You get a better model, you get a more accurate answer. But the latest models for the IPCC AR6 is a divergence because the parameterization are getting so complicated, people are putting extra coefficients. So that's sort of an existential question for climate modeling. Are you getting overly complex? Should we stop tweaking it and stay with where we are? That's an interesting question. But they have diverged. And there are also interesting things about how independent models are. Most climate models are derived from other climate models. Like the IATM model is derived from the NCEP CFS model, which is actually a medium range forecast model. The DOE model actually is branched off from the NCAR model 5 years ago. So models branch off and go off in different directions, and they copy each other's parameterizations. So someone might come to NCAR, see the cloud parameterization, go to UK and implement that in their model. Then the models are no longer that different. So there's a question of model diversity. You want to explore the different parameter space. And if you copy each other too much, you end up with one model, but you don't know if it's right, and if it's exploring the uncertainty enough. So you want model divergence, but not too much. So it's sort of it's an interesting question, how much diversity you want. So that was to give you a feel for atmospheric models. The one thing atmospheric models have been doing for the last 20 years, they resolve weather quite well. And the weather scale is 1,000 kilometers. With a 100-kilometer grid, you can get the large-scale weather systems. You can't get tropical cyclones that well, but large-scale weather systems you can get quite well, like the monsoon flows, you can get it. What could I input to it? Could I have all the information and all the data? Yeah, so why don't you ask me that question when we do the hands-on? That's exactly the kind of question, right? Yeah, I'll answer that question. Just remember to ask me again. So going to ocean models, ocean has the equivalent of weather. If you're familiar with what's called baroclinic instability, that's the fluid instability of atmospheric and oceanic flows. The instability of atmospheric flows has a scale of 1,000 kilometers, and atmospheric models have been getting it, the climate models have been getting it for 20, 30 years. For the ocean, the scale is like 10 to 20 kilometers. The weather scale for oceans is 10 to 20 kilometers. And that you can do scaling arguments to show that it's based on density and stratification. So ocean models also have been typically 100-kilometer grids. So they don't resolve the weather in the ocean, the equivalent of weather in the ocean. These are called mesoscale eddies. So these are like, if you see pictures of the Gulf Stream or ocean current, you see the wiggles. Those are basically manifestations of ocean weather. And typically, our climate models haven't been getting it right, and they had to be parameterized. So this is an example of a model with the 1 degree grid. So remember, 1 degree is 100 kilometers, roughly, it's 108 kilometers. So there's 1 degree in latitude or longitude, it's 100 kilometers. The 1 degree grid, this shows the ocean current surface speed around Antarctica. And you can see this hazy colors showing the velocity. But what if you ran it at 1/6 of a degree? That would be about 16-kilometer grid. You can see all these features. This is the equivalent of atmospheric weather in the ocean, these ocean eddies. If you ever looked at satellite maps of the ocean, you'd see these. The ocean has these very fine features, not just 10 kilometers, they go down to 1 kilometer, and they're called sub-mesoscale eddies. So typically, climate models don't capture this. You can run a high-resolution ocean model for a short period of time and capture this. So people use formulas in ocean models to represent this. I'll show you what the formula looks like. So that's an example of a parameterization in the ocean for the eddies. Now, I'm showing you this because now we actually can cross this barrier and run climate models at this resolution. So you no longer have to parameterize eddies in climate models. So at some point, some things don't need to be parameterized, and you can discard those formulas. In some sense, the model is simpler because you have fewer formulas. You have more grid points, but the formulas are fewer. So conceptually, it's become simpler. And unlike clouds, there's no phase transition involved here. Phase transition really messes up things, but it's just fluid dynamics, and you can cross the barrier and resolve the ocean weather. But previously, this is the kind of formula people used to represent this. In fluid mechanics, you'd call it like turbulence closure. So U is the velocity and rho is the density. You want the flux of density along surfaces of constant density. And so this is the formula. You can make an assumption and write the flux U prime rho prime equal to kappa times the gradient of rho bar, which is the mean density gradient. So this is like a viscosity. So you make an approximation that the flux is proportional to the gradient, which is, if you're doing statistical mechanics, you're familiar with this, like a Boltzmann log. So you make this assumption, you put it in the model, and then you tweak this kappa to get the right results. So this is commonly done in parameterizations. And for fluid mechanics, it works fairly well. When it gets into phase transition, it doesn't work so well. That's why clouds are much harder than parameterizing eddies. So you have various properties. You want to preserve things like energy when you do this, because that's the physical aspect of the system. So this is called a Gent-McWilliams parameterization. So in the 1990s, this was developed to allow heat transport in the ocean to be done correctly. But in the next 10 years, this will be discarded because we got to find enough grid. You no longer need this in the ocean. So coming back to the model of everything, just to repeat what we said, we're trying to predict an out-of-sample event, which we see we have partial observations of, but we don't know whether it's going to go up and how fast it's going to go up in the future. So we start with accurate differential equation for air and water. We had approximate differential equation for clouds and other processes. But we cannot predict human behavior. So we just assume different possibilities and solve the climate prediction for each possibility. That's called projections. You assume humans will act to mitigate climate change. You assume humans will do business as usual and continue to emit carbon dioxide. You try 5 or 6 different things and predict climate for each case and let the decision makers use it any way they want. As scientists, we can't really tell what humans are going to do. But if you give a range of possibilities that constrains the decision making, you know it's not going to warm 30 degrees. Okay. And you know it's not going to warm 0.1 degrees. It's about 1 point, we're already at 1.3 or so. So we give a range and we give detail. You can give detail about each region of the globe. That's just a very important thing that we can tell. And there's uncertainty associated with the detail, but it's better than no information. It gives you constraints of possibilities. So what does a scenario look like? It's great. Sometimes you read a scenario, it reads like a novel. It's not a prediction. People keep thinking it's a prediction, but this is what the wording of a scenario looks like. The particular scenario is called SSP3. And it has a nickname, regional rivalry or rocky road. The scenario description reads like a resurgent nationalism, concerns about competitiveness and security, and regional conflicts push countries to increasingly focus on domestic or most regional issues. policies shift over time to become increasingly oriented toward national and regional security issues. So this is a scenario where nations are competing with each other, not cooperating. The other scenarios where they cooperate, okay? So you need this to predict how much carbon is going to be emitted, because it determines how the economies will grow. And based on this, they use economic and energy models and the integrated assessment models. I'll show you a picture of that, and try to predict how much carbon will be emitted. So there are lots of scenarios, actually probably hundreds of scenarios. Now, each time there's an IPCC report, they add more scenarios. I'm not sure that's useful, you just need a handful. But so you have the SSP1, SSP stands for Shared Socio-Economic Pathway. You have SSP1, which is sustainability scenario. SSP2 is middle of the road. SSP3 is regional rivalry. SSP4 is inequality. SSP5 is fossil fuel development, just going on with business as usual, burning all oil and gas. And this is the latest name. Previously, they went under the name of RCP, so Representative Concentration Pathway, which is technically slightly different. And there are fewer scenarios. And there's a number associated with the scenario, like 8.5. That is the watts per meter squared of the forcing associated with that scenario. So as I mentioned, if you double carbon dioxide, it gives you 4 watts per meter squared globally forcing. So RCP 8.5 says, I think it's within 70 years, it's going to be 8.5 watts per meter squared. That's like quadrupling of carbon dioxide. So 4.5 is close to doubling of carbon dioxide, and 2.6 is less than doubling of carbon dioxide. So this gives you the forcing, and then you have the matrix of scenarios. You can have sustainable low forcing scenario and unsustainable high forcing scenario. So what we do is to make predictions for different scenarios using our climate models. So now let's talk about the carbon budget, and this turns out to be a key part of climate prediction. So carbon is measured in gigatons, and these are the boxes are the reservoirs. So the atmosphere holds 850 gigatons on the average. The land hosts 2,500, the permafrost is 1,700, deep ocean holds a lot, 40,000. But it's mostly there, it stays there. We don't want it to come up to the atmosphere. And this is the exchange between the reservoirs. This in gigatons of carbon per year, just the fluxes. So 120, and a lot of this flux is going back and forth. The plants grow, they absorb carbon dioxide, they die, release it. And what we're adding is a perturbation on the background, okay? And the ocean also absorbs carbon dioxide. If you put too much carbon dioxide, the ocean takes off it. So for every 100 units of carbon dioxide you put in the atmosphere by burning gas, about half goes into land or ocean. About 1/4 goes into land, 1/4 goes into ocean, roughly. So only 50% of what you put in actually stays in the atmosphere. So that's important. Okay, this becomes important when we talk about net zero. So remember this, that there's a lot of exchange going on, and what we're doing is perturbing this flux between different components. There's also longer term over millions of years with rocks. I'm not talking about that. There's a reservoir in rocks, calcium carbonate and things like that, which can absorb carbon very slowly. So what we do is we can do lifetimes of how long carbon dioxide stays in the atmosphere. So we take the reservoir and divide by the flux. That tells you the lifetime, right? So in the atmosphere, the cycling, this is not actually lifetime, this is the cycling time scale. So within 3.7 years, all the atmospheric carbon dioxide gets cycled, but we can actually stay there for 100 years, hundreds of years, I'll talk about in a moment. So cycling time is different for the different components. And for the deep ocean, the cycling time is very long, 400 years. So it takes a long time for the ocean to absorb carbon dioxide. So
these are not facts from your model.
these are simpler models, basically carbon flux models. They're tuned to data, and there's still quite a bit of uncertainty about it. But these are pretty good estimates that about half goes into the atmosphere, into the land, and in the
More complex model will also be
they have to, because we have data to some extent. It's ocean, they measure carbon fluxes. Land, they go to Amazon and set up towers and measure carbon fluxes. So they're based on data, but there's still a lot of uncertainty. We don't have exact differential equations, if that's the question. No, we don't, because these are like microorganisms and particles and trees and
I think the question was that suppose somehow to other means we have some knowledge of some information, then we can use that to calibrate the model.
Yeah, we do that. They do that all the time. They'll assume some kind of a parameterization with a kappa, let's say, and then adjust it based on the data. So what happens if you put a pulse of carbon dioxide in the atmosphere? So let's say you suddenly double carbon dioxide from 400 to 800 parts per million. Any perturbation will decay over time. And this shows how it decays over time. So in the first 100 years, so this is the pulse. The first 100 years, it decays from initially it's 100%, and it goes to about 40% in the first 100 years. And then the scale changes here. In the next 900 years, it goes from 40% to 20%. And the next 10,000 years, so it takes a long time for a pulse of atmospheric carbon dioxide to go away. Even though you have this exchange between the reservoirs, but a lot of it's coming back. So if you double carbon dioxide and stop emitting, go to net zero tomorrow, but you double carbon dioxide, it'll take you 10,000 years to get close to the original concentration. So this is sort of the most worrying graph in climate. The urgency is that if you put stuff in there, it's going to stay there basically forever. I mean, many, many generations of human life, which is the reason people talk about the urgency to act now, because every 10, 20 years you delay, you're putting more carbon dioxide, unless you have negative emission technology, which doesn't exist yet. Even if you stop emitting, this carbon dioxide is going to stay, and greenhouse warming associated with that will continue for centuries to come. And this is something we are reasonably sure of. Again, you don't need the exact number, but you know it's order of centuries. That's enough for us to act. So the integrated assessment models are used to convert the carbon emissions to carbon dioxide concentration, because we had to do with all the reservoirs. And nowadays, actually, these are done in the climate models themselves. But before, they were done separately in simpler models called integrated assessment models. So this is what it looks like. You have population, economy, agriculture. And remember that narrative I had for the rocky road? So you need the narrative to decide what you're going to do in the future with agriculture or with energy. So you use a narrative with this model to create a scenario for emissions, and then you can convert that to carbon dioxide concentration and use it as a boundary condition for a climate model. So carbon dioxide is a boundary condition for a climate model determined by human behavior, which you don't try to predict, you just assume it with different scenarios. And then you use the differential equations of the climate model to predict what the climate is going to do for that particular scenario. So here I'm just going to use illustration of how this works. This is from the previous IPCC report, but the numbers haven't changed that much in the new one. You might have seen this already in my seminar. I showed it earlier. But CO2 emissions for different scenarios is, since it's the previous report, I used RCP, but the SSP numbers are very, very similar. So you have the high emission, medium emission, and low emission. And you can see you project out to 2100. So these are not predictions. People confuse it. They think we are predicting carbon emissions. No, remember the narrative? The narrative determines this. And the narrative is a novelist sitting and writing a novel, right? It's not a prediction. And so we can't associate probabilities with this. People say this is median, this is low probability, high probability. No, it's what is the probability that we'll continue to emit carbon dioxide? That's a question only we can answer. A computer cannot answer that question. Okay. Right. And you think of yourself that you're 1917, right. But this is the problem Divecha was talking about. If you have past data, you can tune your model to reproduce the past. But what's the guarantee it'll work in the future when we have new renewable energy technology? You have to extrapolate. At the very least, yeah, but you remember Divecha talked, you're trying to do 15-year predictions. You can't really predict, even 15 years is trouble. You can't predict 70 years. As I said, we don't try to predict. As physical scientists, we don't try to predict it. We just assume it. So, but I'm not understanding. If I was to start the model in 1970, what would I do reasonable assumption? Yeah. Would I be able to see what I see in 2020? What is reasonable in 1970 is not reasonable today, right? That's the problem. So what's reasonable today won't be reasonable in 2100, but you're extrapolating based on what's reasonable today. But maybe then you use the fact that you saw human behavior that you saw in 50 years. Then will the model replicate in 20 years? Could you say that again? When you say, okay, give specific dates. When are you predicting? When are you starting your prediction? I'm starting in 1970. Okay, based on, you have to use the information available only in 1970. Exactly. You don't know the future. Exactly. Okay, there was no solar energy. There was no electric cars. There was no, when oil was very cheap. And and cars were very inefficient, right?
All of that.
Yeah.
If I make this to be, I say, okay, human behavior is going to be what I actually saw in the
Yeah. Not just human behavior, technology. That's also key. Yeah.
And the idea is to replicate what I see now.
You can probably go look up the literature. People probably publish prediction. Usually they're wrong. Because, usually they're wrong. Because the thing about it is the equation, Navier-Stokes equation haven't changed in 100 years. I mean, that's a fundamental principle of physics, stationarity. And there's evidence for stationarity. Laws of physics haven't changed. But correlations between different components of the economic system depend on the state of the economy. Manufacturing was big in many countries in the 1970s. It's a service industry now. And how much it would have changed, that couldn't have been anticipated. I mean, so that was the problem Divecha was talking about. Even in 15 years, you get a lot of divergence. If you're going out to 2100, you're going to get a huge amount of divergence. Problem, you make some reasonable assumptions. Somebody else makes slightly different reasonable assumptions, and you get a spread. That's exactly the picture he was showing you. So your reasonable is different from somebody else's reasonable. One person thinks India is going to be like Korea, other person thinks India is going to be like Turkey, which is reasonable. Yeah, but so
There's another thing that we know the Navier-Stokes, but we're not solving the Navier-Stokes. We're solving, on a big grid with some forcing added by hand. And
Yeah.
something which we add by hand, we can tune it in such a way that it matches from 70 to now. But those tuning parameters are not going to be good for this.
I mean, you can always tune a model to reproduce what you know, but whether the tuning is valid for the future, it may not be. It may not be. Yeah, that's the problem. As I said, the two ways to predict, either you in sample or you know the differential equations. The thing is, for the economy or human behavior, you don't have the differential equations, and it's unlikely you'll be in sample. If future was going to be like the past, same kind of economy, same kind of distribution of energy sources, similar technology, yes. But you had technological developments, people start working from home and don't commute, all those things, that'll change your.
Yeah. I guess my point is, something I do believe that I can predict,
Right.
but I can't predict human behavior.
Right.
So I feed that in from what I saw.
That's what we do with projections. No, we assume different scenarios and we predict for each separate scenario. And I'll show you a picture in a moment. That'll answer your question, okay? So we have these emission scenarios, and then here. That's a good question. Again, I said, initially it was close to RCP 8.5. Now people think it's close to RCP 4.5, which is not here, but that's pure extrapolation. If you remember the curve I showed, if you have, right. But if you remember the curve I showed, you have a curve. Is it going to go in a straight line? Is it going to go up in a parabola? It's going to become a sine wave. You can't really tell because it depends.
No, I'm asking about 2020 till 2000.
Yeah, well, I guess your question at the moment, what trajectory are we on? At the moment, people think it's like RCP 4.5, which is not here, but it's somewhere in the middle here. But to me, that means nothing. It just means we are on RCP 4.5 now. 10 years from now, we may be RCP 2.5 or RCP 6.5. The fact that we are on RCP 4.5 doesn't tell us much beyond about 10 years. That clearly is the message I got from Divecha's talk, because different people make different assumptions and that gives you a divergence. But the question, do we need to predict? You get a range, so you can act based on the range. Yeah. Right. I'll show you. Okay. Yeah. So this is, so you can convert the emission to carbon dioxide concentrations. And see, these tend to be, this is basically the integral of this. That's why it's monotonic. These are some variable. You can think of this as the derivative of this. And then use that, put in a climate model and predict climate, global temperatures, and you get these global temperatures. And you can see these track the carbon dioxide concentration, not the emission. That's the point. They track the integral. So once you put carbon dioxide, it's very difficult to take it out. And that's why you get this inertia in the system. And you get a spread associated with the different models. You consider different model structures. You get the error bars for each of these predictions. So that's the uncertainty associated with. So you have uncertainty associated with human behavior. That's these three curves. And you have uncertainty associated with models, that's these error bars. So you have uncertainty on top of uncertainty. This is an uncertainty we have some handle over. It's not an exact error bar, but it gives you a spread based on different parameter values. But this is an uncertainty which I don't believe we can predict that, because it's a free will thing. And again, if the economy didn't change and the technology didn't change, yes, we could predict it. But if the economy and technology change, we can't predict it. Divecha, if in 1970, could you imagine what it would be like in 2020, smartphones, the internet, and it's. So what are the different, so the global mean gives you a sort of very narrow view of things. What does it look like regionally? And here I switched to the current IPCC report, so it's slightly inconsistent, but roughly the same answers in the previous IPCC report as well. So here it's a predicted change in temperature for different levels of warming. So the latest IPCC report has gone to called global warming levels instead of projections. And so they look at different levels for global warming and see what it looks like spatially. So here's what it looks like at 1.5 degrees. And the color bar, you can see in some regions it's 4 degrees. It's the polar warming. It's much stronger than tropical warming. So if we go to 2-degree warming, or 3 degrees or 4 degrees, you can see it's very, very warm at 4-degree warming globally. And these are the two scenarios people are talking about when they're talking about net zero to arrest the growth of warming. Yeah, they're aiming for 1.5, but it's unlikely they'll hit that. So more likely to end up at 2. Yeah.
You said in the morning the overturning circulation gets cut off and the
Right.
north pole. Are you seeing that?
No, these models don't simulate those kind of abrupt changes. These are more gradual changes. Simpler models simulate those changes. Again, that doesn't mean it cannot happen, because these models aren't perfect. And these models, one of the reasons they don't show it, these models are tuned to be roughly stable. I mean, my book, I talk about Einstein using the cosmological constant. It's a constant you throw in to maintain status quo, and models tend to do that. They may miss out on some abrupt events because of that, but there's no way around it, because if you don't let them maintain stability, they become unstable right away. And that's not true. So if you tune them to be stable for the current climate, they tend to stay stable for a while. Those patterns are there, but they don't change suddenly. They don't change suddenly. That doesn't mean you can rule it out, but you do the best you can, and these models don't show that. And actually, coming back to the abrupt climate change, the reason I don't think too much about abrupt climate change is to avoid abrupt climate change, we have to go to net zero. To avoid this warming, we have to go to net zero. The solution is exactly the same. Okay, the reasoning for the solution is slightly different, but the solution is exactly the same. If you could see abrupt climate change, you would try to reduce emission to zero. So I don't think, since the answer is not changing that much, I'm not worried too much about the question. So abrupt climate change is possible, but these models don't simulate that. So this is what it looks like in rainfall. And rainfall is much harder to predict than temperature. We talked about that because it depends on clouds, and we parameterize it. We don't resolve it like temperature. And the hatching, these shows where there's no agreement among models. So it's only in a few regions that projections of rainfall tend to agree. There's a lot more uncertainty in rainfall projection of the future as compared to temperature projections. So we're a lot less certain about that. And that's hard because rainfall is often what you want to know. And we have a rough idea, but not the kind of accuracy we'd like to have. So again, you can see some broad patterns here. Overall, the rain tends to increase, but some regions will get less. So drought could get worse in some regions. And we'll talk a bit about it later. You get more intense rainfall because of more moisture, and that adds to the mean rainfall as well. Again, there can be big changes if you get a 4-degree warming. You can talk about 40% increase in rainfall in some regions.
What about monsoon patterns?
We can go back and look. These are, I think, annual rainfall. So, but I guess India will dominate the monsoon. So all of these cases, monsoons seem to be increasing. Dr. Srinivasan, do you have any views on monsoon projections? Huh? Monsoon projections?
Yeah.
I think it's expected to get stronger, right? Yeah.
I'll talk about that.
Yeah, he's going to talk about that. Yeah. So based on this, you can see monsoons are likely to get stronger. I mean, it's sort of consistent with the view that there's warmer temperatures, more moisture, and generally rainfall is more intense. Yeah.
Why there's a decrease in precipitation mainly over Atlantic Ocean?
So this is that's a good question. I don't know the answer, but I can try to guess the answer. And so these are typically subsidence regions where you have the Hadley cell, you have rising motion in the tropics, and you have sinking in that region. And maybe that's because when you get a more intense hydrological cycle, the extremes get amplified. So the wet regions can get wetter and the dry regions get drier. That's, again, I'm guessing here. Someone else may know more about it. Okay, so net zero, that's sort of the phrase of the moment. So let me explain why we talk about net zero. So remember the carbon reservoir, we'll come back to that in a moment, but there's also a heat reservoir in the ocean. And it's very interesting that if you look at the heat capacity of the ocean, 2.5 meters of the ocean equal the heat capacity of the entire atmosphere. The heat capacity of the atmosphere is 10 to the 7. If I get the unit, it's, I think, joules per meter squared. You can just take the C sub P, the specific heat times the mass of the atmosphere. It gives you a rough idea. It's 10 to the 7. And if you take 2.5 meters of the ocean, that has the exact same heat capacity. So this much of the ocean is, so ocean can hold a lot of heat. I mean, ocean's 4 kilometers deep on the average. So it can hold a lot of heat. It also holds a lot of carbon dioxide. It's a huge reservoir. Land, interestingly, has roughly the same heat capacity as the entire atmosphere because it's basically not a very good conductor. The heating and the cooling doesn't penetrate very deep. So if you put an effective depth for land, you get roughly the same heat capacity as the atmosphere. So the atmosphere and land reach equilibrium very quickly. It takes centuries for the ocean to reach equilibrium because the atmosphere is warming the ocean. It takes centuries for the ocean to catch up. And so as I said, there's 4 watts per meter squared imbalance due to greenhouse effect going into the ocean. So that's slowly warming the ocean. It's going to take hundreds of years before it reaches equilibrium. So heat will keep going into the ocean. So greenhouse effect puts 4 watts per meter squared into the ocean, and the ocean absorbs it, and it continues warming. So even if you keep the CO2 concentration at 400 or 410 or whatever it is today, warming won't stop. It'll keep going for hundreds of years. Slowly, but it'll keep going. Sea level will also keep rising because it's sea level expansion of water. So even if you stop carbon dioxide at 400 today, sea level and temperature of the ocean are going to keep increasing for centuries. And sea level, a lot of sea level rise is still to come. And only a small fraction of it has happened already. A lot is still to come as the ocean warms up. And it gets deeper. The heat is getting deeper into the ocean, so it's going to expand the ocean. So when people first started talking about mitigating climate change, they thought, let's fix the carbon dioxide concentration, whatever it is, 400, 420. But that led to something called committed warming, because warming is going to continue. But it turns out, if you reduce the emissions to 0, something interesting happens. Land and the ocean absorb carbon dioxide. Well, half the carbon dioxide that goes in is absorbed by land and the ocean. So if you stop emissions and the carbon dioxide concentration is like 410 today, it's going to start dropping. Because the carbon dioxide concentration is going to start falling because the ocean and the land are going to absorb it. So you get cooling associated with decreasing in carbon dioxide and committed warming associated with the heat sink. It turns out they roughly cancel each other, roughly, again, based on models. So the net result is if you stop emissions, carbon dioxide concentration starts to fall, but temperatures remain constant. So you have two competing effects, and they roughly cancel. So we can stabilize temperature. Let's say you have 1.3 degree warming and we reach 1.5 or 2 degrees. And if you stop emissions, then we can maintain warming at that level. Even though the ocean is trying to warm because of the heat flux, the falling carbon dioxide will compensate for that. So that's why people came up with the concept of net zero emissions. So we can, instead of stabilizing carbon dioxide concentration, you stabilize temperature. And that's what's more meaningful because the environment is affected by temperature. So we can maintain, I mean, there's some degradation, but we can maintain it at that level and not let it get worse. So that's the origin of net zero. And again, this is an approximate because there are big errors associated with carbon sinks. We are trying to parameterize trees, growth of forests, and ocean uptake. So even if we go to net zero, the temperature might still warm a little bit. Oh, zero, okay. Net zero emission is you have emission of carbon dioxide from power generation or transportation. And then they talk about negative emission, like absorbing carbon dioxide using some chemistry, or planting trees and letting them absorb carbon dioxide. So that takes carbon dioxide out. So the argument for net zero is that if you're putting carbon dioxide in, but you're taking it out by these mechanisms, if the net is zero, that's called net zero. But some of these things are very dubious. I mean, there are people selling forests in Indonesia as offsets for carbon emission. Most of those things are dubious. People saying, I won't cut down the forest and call that an offset. It's not really an offset. So that's why I had a question for Dr. Dubas that the net part of net zero is basically abused to get the number to zero. You basically have to get the emissions to nearly zero to stop the temperature from warming. But the reason, this is the reason why net zero is the target. You can stabilize the temperature. And as I said, even at net zero, it might still warm a bit, or it might even cool a bit because of the errors in the carbon budget. But it's a good target to shoot for. What are we doing for time? So I talked about the mean climate change. We talked about the warming pattern with extra warming near the poles. We talked about changes in the mean precipitation. But when you talk about damage due to climate change, it doesn't always come from the mean. Actually, a lot of it comes from extreme events. Extreme flooding, drought, heat waves. They are the ones that cause the most damage. So looking at the mean is not enough to assess how much damage climate change will cause. So you can look at the probability distribution function, which the models will give you. And so typically, you can have a probability distribution like this. And actually, Dr. Srinivasan talked about it a bit. I'll expand on that. So you have a mean distribution for the current climate, and then warming will shift it. So you get extra heat waves, but fewer cold waves. So more extreme. So the first order effect of climate change is to shift the mean. But in a nonlinear system, you can have a higher order effect. So you can also change the variance of the probability distribution. Then even if the mean doesn't change, you get more extreme. In this case, it'll be symmetric. You get more cold weather and more hot weather. And there are nonlinearities in the climate system. The biggest one is moisture. If you put moisture, I mean, rainfall is a positive definite quantity that immediately makes it nonlinear. And moisture is positive definite. If you put moisture in, it amplifies the strength of rainfall. And that is an inherent nonlinearity in the system. And that can give you not just a shift in the mean, but a nonlinear change in the variance as well. And that's one of the reasons you get much more intense rainfall in warmer climate. It's a nonlinear feedback of moisture. What happens is you get air rising in a cloud. And when air rises, the moisture in it condenses and heats the air around it, and it amplifies the rising motion. That's how clouds form. And when there's more moisture, that amplifies the process. And if you're familiar with basic thermodynamics, the Clausius-Clapeyron relationship says for every degree of warming, you get 7% more moisture if you linearize it about our current temperatures. So it's a huge increase in moisture for every degree of warming. And that amplifies the local rain events. Actually, it turns out globally, you don't get a 7% increase. You won't get more like a 3% increase for global moisture budget because the upward motion also changes and that compensates for the 7% rise. So globally, the change in humidity is more like 3%. But for extreme rainfall, it's a local effect and it's a lot greater than 3%. You get a much bigger effect locally. So from basic physics arguments like that. And models can simulate some of that. They still have trouble getting the extreme rainfall, but because it happens in cloud scale, you don't still resolve the clouds. So there's still a lot of uncertainty about how the tail of this will change for really extreme rainfall because you don't simulate those processes. And same is true for tropical cyclones. A 100-kilometer grid will not really simulate tropical cyclones very well. So you can have increase in variance, and you can have a combination of increase in variance and increase in mean, which is more like what happens in a combined system. So I put in a few figures from the latest IPCC report, which was released in August. So what they have here is how extremes change in different parts of the globe. I'll zoom in on India in the next, so don't try to squint too much here. I'll get a bigger view of this. But what each of these shows is for different levels of warming in the x-axis, the number of frequencies of increase in 10-year events or 50-year events, so extreme events. So you can see as the warming goes up, these 50-year events are getting much, much more frequent. And so are the 10-year events. So you can see that if you look at the IPCC report, you can see it globally, but let's look at, say, India. So you can see this increase in India in the 50-year events in temperatures. These are heat waves. So you get these increase in heat waves over time. And so in addition to the mean change, mean warming, the change in the extremes is a big factor in the damage due to climate change. We can do a similar graph for rainfall. So again, for different regions of the globe, you plot this and you zoom in on India. So again, you get this increase in extreme rainfall events as the temperature warms from 1 degree to 4 degrees. Again, there's still quite a bit of uncertainty with rainfall extreme because our grid does not resolve those intense rainfall events. So there was a question about how many climate models are there. This is for the latest IPCC report, I think. It's a map which shows the major climate modeling centers. As I said, US, there are 3 main climate models, but there are also smaller ones, variations of the main ones. Several in Europe, 1 in India, a few in China, Australia, New Zealand. I guess South Africa has 1, Brazil. And so roughly about 30 or 40 models that go in. Which one?
This one.
Yeah?
No, the
Oh, this
very
one.
left one.
Oh, this is just a repeat of the, I got the map. It's a wraparound map. I tried to cut it off, but they're both New Zealand. Again, if you went back for 10 years, China really didn't have any models, but Europe and US had models. US models actually have been decreasing slowly. The computers needed to run them getting bigger and bigger. So how do models change over time? In the mid-1970s, we had atmosphere, land, ocean, and sea ice. These were the components. And the first assessment report here, we didn't have aerosols. Aerosols are the small particles in the atmosphere that can reflect sunlight typically. Sometimes they can absorb it, but typically they reflect it. But they also change the properties of clouds. But they started putting it in models from the second assessment report. Carbon cycle started getting into models in the last 20 years or so. Dynamic vegetation, like the greening of Sahel, which the vegetation can interact with the climate and change the albedo. So that started getting put into models, atmospheric chemistry. And the latest is land ice, like ice sheets of Greenland and Antarctica. So this is how the complexity has been increasing. I think I'm going to stop. I have a few more slides, but I can I'll basically stop here. No, I'll do this few more slides. This is sort of the state of the art in climate modeling. So this is from the NCAR model, which shows the latest additions, which is ice sheet models. These are different versions of the Greenland ice sheet. And this is sort of a regional model for comparison. And this is something called surface mass balance. So one of the tricky issues with ice sheet modeling is that typically if you put an ice sheet in a climate model, it'll either snow too much or too little. And then either ice sheet will start disappearing or start growing too fast. So if the mass balance is incorrect, it'll quickly either grow or disappear. And ice sheets do change, but they don't change that rapidly. So models, so it took a while for people to adjust the mass balance right. So it grows or decays at observed slow rates. So this is the mass balance. The blue is getting thicker and the red is getting, this may be evaporation. I guess you have melt at the sides here. And this for Antarctica. So this is sort of the latest addition to climate models with ice sheets. And I said, people are trying to go to very high resolution in climate modeling. So this is probably the most advanced effort right now, which is the Department of Energy climate model. So they have a new version of the model called SCREAM, a simple cloud resolving E3SM atmosphere model. And I don't know if you can read it, but they're trying to run it at 3 kilometers on GPU architectures to get the performance. And here, most climate models are hydrostatic. If you're familiar with fluid dynamics, you can ignore the time derivative of W, the vertical motion, because the scale is 100 kilometers. But once you get down to 10 or 5 kilometers, the vertical motion becomes important and you need a separate equation for that. So these are non-hydrostatic models of 3 kilometers. So we have to rewrite the equations. The equations are different when you go to non-hydrostatic. Many weather models actually are non-hydrostatic, but the climate models typically are hydrostatic. So this shows a picture of what's called an atmospheric river. It's a stream of moisture coming in from the Pacific to the west coast of America. It hits the mountains and creates a lot of rain. And so the goal is for this type of a high resolution climate model to capture this process and get the extreme rainfall associated with the atmospheric rivers correctly. I'll say a little bit about the limits of computing. I mentioned the CFL criterion. Compute time increases like the 4th power. So if you double your linear grid, you need 2 to the 4 or 16 times more computing. And computers have many nodes. And what happens is if you start distributing the work among different nodes, if you don't have enough work for each node, that means it has to communicate frequently, that slows it down. So arithmetic intensity is the ratio of floating points to memory access. It's measured in flops per byte. So if your arithmetic intensity is low, even if you have a lot of processors, you don't get the full performance of the processors. So that's a bottleneck in climate modeling. So you could have a computer with about 4,000 nodes. That's kind of number of nodes you have. And each node might have like multiple processors. You might end up with 600,000 cores. You might have 4,000 nodes and 600,000 cores. That's the typical numbers, or maybe 200,000 cores. So each node may have like 60 cores. But if you distribute your grid points, but there's not enough grid points per core, then there's too much communication between the nodes and it gets slower. So typically climate models only use about 5% of the capacity of a machine. So the fastest machine in the US is Summit, which I think has a peak performance of maybe 200 petaflops. That's the peak from the manufacturer. If you do linear algebra calculations, it's called LINPACK, you might get 140 petaflops, so 70% of the peak. A climate model would barely get 5% or 3%. Because what happens, linear algebra, you're doing matrix multiplications. It's very deterministic, predictable sequence of operations. And it's similar to like the GPUs were invented for video games. So video games, you have like, you're rendering an image with shadow. You have these rays and you apply a matrix to see how the shadow appears. It's very predictable. There's no uncertainty there. And the GPUs were optimized for matrix operations and they do very well. But in a climate model, you don't just do matrix operations. If you're doing rain, you decide if there's enough moisture, if it's saturated. The if statement, we said if this is true, rain, if not, don't rain. So it's not predictable. And so when it switches between these states, it stops the GPU, and GPUs are not that efficient at handling the non-deterministic computations. So you end up with very low utilization. And so this is a graph that shows for the DOE model, simulated years per day. It's a performance. So if you simulate more years per day, you're performing better. It's a number of nodes. So if you take the same problem in the atmosphere, ocean, or ice, discretize it and solve the partial differential equation, and put it on more nodes. It's the same problem, but putting it on more nodes. So initially, as you get more nodes, you get linear scaling. You get better performance because you can get more computation done. But at some point, there isn't enough work for each node, and the communication becomes a bottleneck, and you saturate. So you could use up the entire, let's say you're using 1/4 of the computer, you're getting a certain performance. But if you saturate, you could use the whole computer to get the same performance, you get nothing. What you end up doing is you run multiple jobs at 1/4 of the computer because there's no point trying to use the whole computer. So scaling is a big issue when it comes to these models. So trying to maximize the use of computers. Well, one solution is to go to higher resolution. Then you get more work. But then you won't be able to run a 100-year simulation. So it's a trade-off there. A couple of other things, there's something called Moore's law, which says that transistor density doubles every 2 years. And if you've been buying laptops for 20 years, you might have noticed that. I don't know. When I first used to buy laptops, you'd get 1.5 gigahertz or even 500 megahertz. And then it became 2.5, 3.5. Now you get 4 gigahertz processors. But it's basically saturated. And if you notice, what you get are you get more cores. Before, you would buy a laptop with 1 CPU. Now you get 8 cores. Because the transistors are getting so small that they can't make them any smaller. It's like 7 nanometers or 9 nanometers. But they're putting more CPUs and trying to get you more performance. But it's not the same thing because you have to distribute the work between different CPUs. But so Moore's law is basically ending. So that's limiting the speed of computers. There's something called Dennard scaling, which is that as transistors get smaller, the power density stayed roughly constant. If you remember physics, power is voltage times current, V times I. So as transistors got smaller with Moore's law, V and I scaled so that V times I remained the same. So you could build chips which didn't emit too much heat. But Dennard scaling already broke down because you can't get your current down too much below the noise level of the chip. So what happens now is the chips are generating awful lot of heat. And if you ever looked at a chip, it has a giant fin that get the heat away from the chip. So you're not able to get the heat out, and that's a basic limitation on computing. And so that's why GPUs were developed. GPUs are low power, they do operations slowly, but they do lots of them at the same time. So computation has shifted towards GPU computing, but GPU computing is not optimal for climate modeling. It's good for graphics and linear algebra problems. So one of the ways to get around it is to try and use machine learning to, instead of solving the differential equations using a time stepping scheme, try to go from one time step to another, but you don't have to follow the CFL criterion anymore. You could go faster than that if you can get it to work. So people are working on trying to do weather forecasting using machine learning. They just give weather maps to this computer, predict next day's weather map, and give thousands of weather maps and see if it can learn from that. Potentially, that's possible. Yeah, deep learning. So those are things people are working on. Certainly for weather, it could work. Whether it'll work for climate, we still have to wait and see. This was just a picture of Moore's law. I think I'll just skip to the end. Out of time. Oops. Get. Okay. So unprecedented events can be predicted if you know the differential equations. That's sort of the key takeaway, that when you're trying to predict an out-of-sample event like global warming, you can't rely on statistical models. You need differential equations and solve them to get a global pattern of warming. It's not exact, there are a lot of approximations, but that's the best we can do. And we're lucky in the sense we have differential equations for climate. We don't have it for human behavior, but we have it for climate. So we assume different scenarios for human behavior. So we don't need a model of everything. We need a model of the important things. And as model complexity continues to increase, you have lost the sharing. So more grid points can give you better hurricanes and mountains. That's kind of obvious. But I skipped over the slides, but increased complexity also leads to increased spread in something like climate sensitivity, or the warming associated with doubling of carbon dioxide. So it's sort of a double-edged sword that you get better features in some ways, but the uncertainty isn't decreasing because you have more undetermined parameters in the system. And when you consider a range of those parameters, you get more uncertainty. So you're not getting convergence in the warming. You're getting detail, but you're not getting convergence. And we're hitting the limits of computing, and whether things like machine learning can help us beyond that, that's an open research question at the moment. Thank you.
Very, very informative. Very nice. What we can do is first, let's take the questions from online. If somebody wants to put a question on chat, because we can take a few questions offline, but that can carry on over the tea break as well. So if someone has a question online, this would be a time to maybe unmute and chat. Okay, if there aren't, then are there any questions amongst the audience here?
So that's a good question. I skipped over it because there wasn't enough time to go into that. Models actually, we take into account internal variability. So what we do is we do an ensemble of predictions. We don't do a single prediction for a particular projection. Typically, you need a pretty large ensemble, about 50 members. And some climate modeling centers are doing that. So you can capture the spread of internal variability. So you get the statistics of internal variability. But the real world has signal plus noise, right? It has the global warming signal, but it's one realization of the noise. There is no way we can predict that. So it will happen that the real world warms more than predicted or less than predicted in the next 50 years. It'll go up and down. We can't predict those ups and downs. We can only predict the smooth trajectory. But we can predict the spread using an ensemble of models.
Hi, thanks for the. I had a question that you said that the models are diverging a lot now in the last IPCC report or so. So do they also diverge for historical forecasts, or is it for the future?
That's a good question. So what people found was that the models that diverged the most in 2100 were also diverging in the historical forecast. So there seems to be some correlation.
It's not that the climate has become more unpredictable, because the forcing has suddenly increased, right? I mean, this massive CO2 is let's say a big forcing which we are putting into the system.
Right.
So it's not an increased sensitivity of the climate.
Well, they're two separate questions. One is the model spread, I think, is real, and it's a problem of the models. You're asking the question, is climate sensitivity time dependent? So climate sensitivity, I didn't define it, is how much would the climate warm if you double carbon dioxide today? Okay. So let's say the current estimate is about 3 degrees. If you double carbon dioxide today, climate will warm by 3 degrees eventually, equilibrium. It'll take a few hundred years to reach that. But the question is, if I double carbon dioxide 1,000 years from now, would it still be 3 degrees? So it could be time dependent, right? And there's something called the pattern effect. So the pattern of sea surface temperature change affects climate sensitivity. How much clouds are there in the tropics? So there's a real state dependence of climate sensitivity. And we don't know that yet, but you can see that in models. To the extent you trust the model, you can study it in models, but the models are diverging. But so I think there were two questions in your question. But just the divergence in the models is, I think, a model artifact. It's not a reflection of the real state dependence of climate sensitivity. Thank you. So normal subgrid parameterization is just a formula. I mean, I gave you an example of flux equals kappa times a gradient. That's a typical subgrid parameterization. Cloud subgrid parameterization is usually more complex. They usually have plume models and put some coefficients and turbulence models to come up with that, put some phase change in. But it's just a formula. I mean, it's expressed as a Fortran subroutine. But there are people doing something called super parameterization. So what they do is, in each grid box, they run a two-dimensional cloud model. So it's a model within a model, but since it's two-dimensional, it's cheaper. I mean, if you can't run a three-dimensional model within a grid box, because you might as well run the whole model at that resolution. But what they do is run a two-dimensional model to represent clouds. But the problem is you're assuming the clouds are two-dimensional. It's still sort of research area. People think it produces better rainfall, but it's a pretty drastic approximation to treat the clouds as two-dimensional. But those are called superparameterizations. They run a simpler model within the grid box.
So maybe this question is slightly off topic, but are there any efforts to improve computer architecture to a better compute climate models like that?
Yeah, that's also a very good question. Right now, it's interesting because climate models used to drive computer architecture until video games became popular.
Okay.
Really, because the climate model, like Cray, or they would come to climate modelers and say, let's benchmark your models on our model. And they used to be important customers. Because the customers were like defense industries, oil exploration use supercomputers and climate models. They're the big customers. So the supercomputer makers would come climate modelers and so the original, they had fast processors with fast interconnects for supercomputers. But once video games became popular, that's a huge market, much bigger than any climate modeling market. So that drove computer architecture, and GPUs became popular. And then people figured that you can use GPUs to do machine learning, and machine learning is a hot topic. So GPUs for machine learning are the most popular driver of computer architecture, and climate modelers have lost their say. Be a slave to what the GPU manufacturers make. But there are a few people trying to design custom chip architectures called FPGAs. I forget what it's, programmable gate array, I think. Flexible programmable gate array. But you could design custom chips to solve the equations you're trying to solve. But it's a pretty small effort. And people trying to do low precision arithmetic, you don't need 16 digits accuracy for a certain prediction. You might be happy with 6 or 7 digits because there are other errors that are going to mask your floating point accuracy. So you could define different architectures which are more efficient for that. So a few people doing that. For the most part, the big computers are being driven by GPU manufacturers, NVIDIA or AMD.
Okay, thank you.
I have a couple of questions about the parameterization. So firstly, you said that if we go to a small enough grid, maybe we eliminate the need for some parameterization and we simulate these processes directly. So what are the processes that we cannot achieve this with? And secondly, are the parameterizations really so bad? Because like if you tell me that you cannot predict that this cloud will rain, I believe you. But for a climate model, we just need the overall statistical picture.
Right, okay. So you have two questions. The first one was, just remind me of the first one? Second, okay, let me answer the second one. The problem with clouds is it's a small difference of large numbers, right? You have stratus clouds, which reflect sunlight and cool. And you have cumulus clouds, or cirrus clouds, which trap infrared radiation. And each of them maybe you can simulate it for weather. You can simulate the large numbers. For climate, you're talking about the average of the large numbers. So any small error in that will affect climate. So whether you can get clouds right for weather is a slightly different question from whether you can get it right for climate, which is a harder problem. Which is why it's harder to simulate clouds for climate, I think. I lost your first question. Can you just repeat?
I think the first question was, even if you make the grids finer, if you make them finer and finer, are there some things which you cannot predict?
Okay, I alluded to that. I showed you the ocean eddy parameterization. There's no phase transition, it's just fluid motion. And I think you have parameterization, once you resolve it, the parameter, you can throw it away and you don't need it anymore. Although people got rid of mesoscale eddy parameterization, but they're talking about sub-mesoscale parameterization now. So it's sort of a never-ending game. But for clouds, it's a bigger problem because things happen at all scales. You have raindrops on millimeter scale, then you have micron scale nuclei. And so even if you're resolving the cloud, you have microphysics. And you can have different microphysics parameterization. And if they affect your cloudiness, you still get an uncertainty. So we don't know, we won't know it till we get there.
Okay, go ahead.
Hello. You mentioned that clouds are hard to simulate in the grid because the grid spans, let's say 10 kilometers or 100 kilometers, and clouds are smaller than that. But if we take a look at volcano eruptions that start at say 1 or 2 kilometers of the order, and its effect spread globally, not globally, but larger than the starting point. So how do you incorporate the volcano eruptions and the effect of that into the models?
Well, in climate models, volcanic eruption is basically a plume. Okay, so cloud is lots of different plumes of lots of different sizes. So, I mean, I think fluid dynamics, they try to model plume, but climate models, they don't even model the plume. They just model, they find the total amount of aerosol that's coming out and just put it in the stratosphere. Climate models don't do the actual plume of the volcano. They use some other satellite estimates. So many, a million tons of sulfates were released. And once it gets into the stratosphere, it spreads out very quickly. So you put it in there and then you study its effects. So I don't think they have actual plume models of volcanic eruptions. I mean, it's not, you don't need it anyway. Yeah.
Okay. I guess we should take this question from Sumit Mukherjee. Sumit, do you want to unmute and ask your question, or?
Yeah, hello, sir. Am I audible?
Yes, you are.
Yeah, good afternoon, sir. So my question is that how reliable are non-hydrostatic climate models in projecting systems with rigorous vertical velocities, like the cyclones in the future scenarios, climate scenarios?
I didn't fully get the question, but I think you're asking how reliable are non-hydrostatic climate models in predicting something like tropical cyclones, right?
Yeah, the systems which have rigorous vertical velocities. I mean, in those systems, the vertical velocity needs to be computed much detail.
Right, right.
The non-hydrostatic climate model, as I understand it, is not doing good.
Well, to start with, non-hydrostatic climate models don't exist yet. They're being built. And so they have a 3-kilometer model under development, but to run it like 100 years, it's probably going to be 5 years before they're able to do that. They're still running it for very short periods. But we use non-hydrostatic models for weather prediction. I suspect that IMD uses non-hydrostatic models to predict tropical cyclones with a regional model. So all the regional hurricane prediction models typically are non-hydrostatic. So we know quite a bit about how well non-hydrostatic models to simulate tropical cyclones. They usually do the track pretty well. They still have trouble with intensity. That's a well-known issue. Predicting intensity of tropical cyclones is not a solved problem yet. Often they rely on statistical models as much as they do on physical models. So that problem won't go away because we have experience with running models at 3 kilometers for weather. But right now, a 100-kilometer grid climate model cannot get a tropical cyclone, really. It gets a poor approximation to it. So I think we will do better, but how accurate will be, I don't know. I don't know that. Because we still have problems getting the intensity right, even in our weather models.
Okay, so thank you for the clarification.
Okay, I guess we should probably head for tea now, and if there are any more questions, we can take it up there. The way to make up for that is we'll now meet at 4:30. So we'll meet half an hour later.
Yeah, I don't have that much material for the second part, so we can cut it short, yeah.
And even if you need further time, we have a slot tomorrow, so we can take it up.
It's going to be a sort of brief view of what's out there.
Okay, good. So we'll meet at 4:30, and like I said, if we need to meet again, we have some time slot tomorrow. Thank you very much. One more time.